So let us continue with our reasoning on in the probabilistic domain. So in the earlier part we have seen how to model a system and what are the things we can do, and that step we have actually looked into in the previous part. In this part we will take a more concrete example and we will try to determine some of those probabilities, and for which we will take one of the classical example. You will find the similar step in many textbook, this example. So so let us uh, look into this classical example. So the information that is given to us is that there is a burglar alarm at a home, and uh, it works almost perfectly. Sometimes alarm goes off if there is an earthquake also. So that is from the alarm side. So when it can actually turn off, when it can actually goes off. So there are two neighbors. So one is John. John can call police when he hears the alarm, but sometimes he misinterprets telephone ringing as alarm and calls police too. The other neighbor Mary, who also calls police, but she loves loud music, therefore she misses the alarm sometime. Now, in order to model this problem, we need to find out the variables and the probability for those variables, and we need to represent the stuff in a compact manner. So we'll be trying to find out the dependency between those variables. So the variables that can be here is like there can be a burglary. So maybe I can use a different color. So there can be a burglary. So if burglary happens, then certain things get activated. So if burglary happens, then my alarm can actually go off. So alarm is another variable, but this alarm can be triggered by earthquake also. So earthquake can be another variable that influence the alarm. Now, based on the alarm, John can actually call the police. So John calls police can be another event, but so he can calls the police, but sometimes he misinterpreted the telephone ringing as the alarm as well. But so the thing is, either he identifies it, it is the alarm that goes off, or something else. So we try to assume these two are mutual different events. So if the alarm goes up, then telephone ringing is not there, and if the telephone ringing is happening, then alarm is not there. Similarly, for Mary calls police, so this is another event, but so with 100% certainty, she does not call the police because she loves loud music, so she can misinterpret some of the alarms as well. So typically we will have this five variables. So it is the burglary, it is the alarm, earthquake, John calls, Mary calls. So now let us try to create the dependency information or the qualitative information before we proceed for quantitative stuff. So burglary is definitely one of the event. The next is the earthquake, and burglary and earthquake are independent event that we can easily understand because they will not have any kind of correlation. Then the alarms can goes off, so alarm is the another variable. The other two variables are John calls and the Mary calls, or the events that we can see. Now for the dependency part, the if there is a burglary, then the alarm can go up. So definitely burglary will influence the alarm. Similarly, earthquake can also influence the alarm. If the alarm goes off, then John can actually call police. Also, Mary can actually call police. So we can construct the qualitative information in this manner. So this basically represents some kind of a dependent stuff. Like, so there is a relation like burglary. If burglary happens, then alarm can go off, and if alarm can go off, then Mary can call. So that is one of the possibility. But burglary, earthquake are independent, and and there are many other things we would like to reason about. We would like to do some kind of an analysis on this framework. So once we compute this one, we have to go for quantitative information. So for quantitative information, we have to give the probability values. So what is the probability that the burglary can happen? So it can happen with a probability of 0.001. Similarly, for earthquake, the probability is something like 0.002. Interesting to note here that the earthquake probability is more than the burglary. The reason here is in this classical example, the person who developed this example, he actually belongs to a place where earthquake is more frequent. Okay, so leaving that part apart, similarly we can proceed for other conditional probability table. For burglary and earthquake, it is not there is no condition because they are the independent event. But for alarm, this alarm can goes off uh, when the burglary or the earthquake happens. So I have to provide a conditional probability table, and for every combination of burglary and earthquake, I have to provide the probability that the alarm goes off. So if you look into this situation, this entry in the table, this basically says that if burglary happens and if earthquake happens, then the probability of alarm goes up is 0.95. So there is a probability that even if the burglary happens and the earthquake also happens, but the alarm does not go off, the probability is less, and that probability is given by 0.05. So we can determine that stuff by looking into this value. Similarly, for the other entries in the conditional probability table, like if burglary does not happen and if earthquake does not happen, then the alarm goes up. It has a very uh, low probability, which is expected one. Similarly, we have to provide the other values like probability of John calls, but that will be conditioned on the alarm. So we have to provide those two tables. Now, one thing to note here is um, for this set of 5 variables, we can represent the probability of the stuff using only this 5 tables. Now this belief network actually is a compact representation of the joint probability, because I could have mentioned the joint probability including all these 5 terms in a single row, and then I could have expressed that stuff. In that case, I need to have 2 to the power 5 number of rows to represent the different combination. Now if you look into this one, then we have just used 1, 2, 4, 6 and another 4. So we just use only 10 rows to represent the actual fact. So belief network, if you can represent the system in the belief network, then it can save a significant amount of space, and we can represent the actual behavior in a succinct manner, and it is actually very compact. Now we will look into the how we can utilize this information to find out certain probabilities. Now, probabilities in belief network, if you would like to determine, then it basically uh, represent the joint distribution, but not explicitly, but in an implicit manner. So if we combine this local conditional distribution, then I can actually determine the joint probability distribution as well. So only thing, we have to multiply the appropriate conditional probability so that we can determine the joint probability distribution. So when we are interested in finding out the joint probability, this means that we'll be interested in order to find out this value, and this expression has to be broken down as a multiplication of few conditional probability values, so that we can determine the required step easily. So let us look into some of those examples. So let's uh, say somebody has given me our stuff. So burglary, earthquake, alarm, John calls, Mary calls, and all those probability values that we have seen earlier. Now somebody wants to reason about these queries, like probability of the event that the alarm has sounded. So effectively I would like to find out A, but neither a burglary nor an earthquake has occurred. So effectively I would like to find out not B and not E, and both Mary calls and John calls. So effectively I want to find out the probability or the joint probability where A happens, B does not happen, E does not happen, but M and J both happen. Now in order to find out that probability, we uh, we can say we can compute in this manner. So it will be nothing but P of this expression, because uh, we have already said that alarm goes off, Mary calls, John calls, but burglary and earthquake does not happen. So in order to determine this one, we can break it up into the conditional probability stuff, and we'll be using the chain rule, and we'll look into the structure of the belief net. Based on that, we can actually compute the stuff. like like in this case, when I say probability of J and M and A and not P not E, I can represent that stuff in this manner. So let me write here. So I can say probability of J, uh, probability of J given probability of M, A, not B, not E, times probability of M, A, not B, not E. So we using this expression, uh, we can actually proceed. Now if you look into this stuff, then then if you if you look into this stuff, let's say this part of this thing, then here it is given that alarms goes off, or I know the situation of alarms. So J is dependent on only J is dependent on A. Now if somebody gives me that A happens, then I am not bothered about, or if somebody says the condition about A, then I will not look into B and D, because this is conditionally in. So if A is given, then J can happen. So B does not have a direct influence on J. So B influences J through A. So if information about A is given, then J is solely dependent on A. So this part I can simply write P of J given A. Similarly, on this side, I can, if I proceed in the same manner, I can actually write this will effectively turn out to be M given A, and effectively I will left with A not B not E. I have to determine the probability of this stuff. Now if I want to find out the probability of this, then it will be probability of A given probability of not B and not E, this expression, times probability of not P not E. Now probability of not P and not E, when I try to find out the probability for this part, then these two events are independent because none of them influences each other. So effectively I will get, it will be P of not P and P of not E. And now once I get this full expression, the interesting thing is all the values are available to me, and I can actually proceed in this. I can just look into the conditional probability table and I just replace all those values and I get my desired stuff. Like P of J given A, it is given to me. P of M given A, it is given to me. P of A given not B not E, so this is this value, and so on and so forth. So I can actually use those stuff and I can determine the value. So effectively what I have done, I have determined the joint probability values from the conditional probability stuff, and we have exploited the dependency information or the qualitative information from the belief net. Now let us look into some another example. So let's say we would like to determine probability of A. Now probability of A, when I want to determine, then probability of A actually depends on B as well as E, because if you look into this one, A is dependent on B and as well as on E. So but definitely I do not bother about J and M because they are not influencing A. Now if I want to determine probability of A, then I have to look into uh, all joint probability stuff that A, B, E can actually generate, because A is dependent on B and E, so B and E can influence A. So I have to explore for all combinations of B and E how A is happening. So in order to do that, we have to determine the values for this expression. So probability of A can happen if A happens and B both do not happen, B do not happen, E happens, uh, B happens, E does not happen, and both B and E happen, and as well as A happen. So these are the possibilities under which A can actually happen. And now we can expand this expression to find out the conditional the probability for A. So we can expand in the same manner. So it will be probability of A given not B not E times probability of not B not E. Similarly for the other one as well, and we can proceed in the similar manner. So now interesting thing is that this value I will get from the table, the conditional probability table, and these two events B and E are independent, so I can use the independence rule and I can find out probability of B and E. So it will be just multiplication of B times PE. So we can exploit the conditional probability table, and by looking into the diagram we know which is independent of what, and we can find out the actual probability. And this turns out to be these values, so you can work on that part. Now let us look into, say I want to determine probability of J. Now if I want to find out probability of J, then J can happen under the influence of A. So if I want to find out this Pj, then I have to explore uh, probability of J that A happens and A does not happen. If we can find these two values, then I know probability of J, because only A is influencing J. So so there are two possibilities for P of A. So under these two circumstances, if I can find out with what probability J is happening, then I can find out P of J actually. So effectively I need to find out P of JA and P of not J, sorry, P of J and not A. So if we proceed in this manner, then we will get a value something like this. And if we need to find out P of not A, then we can use 1 minus P of A, and this value we have determined in the previous slide, we can reuse that stuff. So that will be my probability of J. Let us proceed in this for few more examples. Let's say I want to determine P of AB. So so A is influenced by B, A is also influenced by E. B has no influencer. So so in order to determine P of AB, we have to bring in E terms as well. So AB can happen when AB happens as well as E happen, or AB happens and E does not happen. So under these two scenarios, AB can actually happen, and I do not bother about uh, uh, whether John calls or the Mary calls, because those are dependent on A, so we do not have to look into that stuff. So we can proceed in the same manner. So we have to find out P of ABE and P of AB not E. Since these two are mutually exclusive, so I just need to add the probability of this one, and we can actually find out this probability values by doing this mathematical calculation, numerical evaluation. So let us take a look into probability of JB. So if I try to find out JB, then definitely I need to introduce A, and if I if so it will be probability of JBA and probability of JB not A. Now in order to determine this one, what I need to do is probability I just expand in using the uh, normal rule, like P of JBA, probability of J given AB, probability of AB, similarly the other one as well. Now if I proceed in this manner, I come to an expression something like this: probability of J given A, probability of AB, and probability of J given not A, probability of not A and B. Now here, since we have computed earlier P of AB, so therefore we can use that value directly. We can use that value here, and we just need to find out in a similar manner how P of not A, B is, what is the probability of not A and B, using the same technique. And for that I have to introduce the variable E. Here we have not shown because we have already computed P of AB, and we can follow the similar steps, and then we can determine the stuff. Now if I want to determine probability of J given B, now we can proceed in the same manner. So it will be probability of JB given probability of B. So probability of JB we have just determined, so which will be 0.00086 by probability of B, which is given from the conditional probability table. So I can say that John calls given the burglary is 0.86. So which is good enough that if burglary happens, then John actually calls the police. So with a high probability. So which is somewhat logical. Now, just to elaborate few more things, like sometimes we do diagnostic inference, like say given that the John calls, so what is the probability that the burglary happened? So if I want to determine that stuff, then it is given. So I know that John has called. I have to find out what is the probability that the burglary actually happened. So we have to determine P of B given J, and that we can proceed in the same manner and we can determine the actual value. The other kind of relation that we are also interested to explore, like the causal inference, like causes to effect relation, that given the burglary infer that the John will call. So with a very high probability John will call with 0.86. Similarly, if the given that the burglary happens, then what is the probability that the Mary calls? So again we have a very high probability, 0.67. So so this way we can actually analyze our system. So we can also proceed in a similar manner, like intercausal inference, more complicated one, like say given the uh, alarm and we want to identify with what probability the burglary has happened. So if the alarm goes off, then what will be the probability that the burglary actually happened? So it will be P of B given A. So if we determine, it will be 0.376. Also it may happen that, like if it is given that the earthquake is true, so what I mean to say is from with respect to this event that the alarm goes off, and somebody has told me that alarm goes off and the earthquake happened, uh, then what is the probability that the burglary actually happened? And so it will be probability of B given A and E. And if we determine that probability, then the is a very small probability. Like if the earthquake happens, then probably the chances of happening burglary simultaneously is less. There can be a mixed inference stuff that we can look into, like John uh, John actually calls the police, and given that also that earthquake does not happen, then what is the probability that the that the alarm actually goes off? So 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 effectively we need to find out P of A given J and not E. So we can find that thing out, and the probability is something like this for this example. So so with this kind of stuff we can actually say that given the belief net and the belief net, which has the conditional probability table, the quantitative information, and the qualitative information, the dependency part, we can determine the joint probability, or we can determine many conditional probability. We can query on the stuff, and we can actually we can figure out some of the causal relation, or which is related to what with what probability. And if we observe certain outcome, then we can try to do some kind of a diagnostics that if John calls, then with what probability that the earthquake actually happened. So this kind of diagnostic stuff, or maybe a complicated stuff, we can actually reason, we can actually query, and this is a kind of a compact representation, so which is one of the most important thing, and this can be used for answering different kinds of queries. So thank you very much.